Hello and welcome back to another homework video. So today I'm going to talk about diffusion in vapor and liquid binary mixtures. So then to start this video, we want to estimate the diffusion coefficients for vapors and liquids. So for that, to have a rough estimate, most chemical engineers will say that vapors the diffusion coefficient is around 10 to the negative fifth meters squared per second, whereas liquids are around 10 to the negative 9 meters squared per second. So that's just a rough estimate, but we're going to look at more accurate ways to estimate the diffusion coefficient. So to do this, we're going to use the Leonard-Jones potential equation. Okay, so this is going to say that the diffusion coefficient of component A through B is going to be equal to 0.00266. This is a constant that was determined experimentally. So we have that times the temperature of the system to the 3/2 power. And this is going to be over the pressure of the system times the molar mass of component A and B to the 1/2 power. So that's basically the average molar mass. And this is going to be multiplied by the collision diameter of A and B squared times the diffusion collision integral, which is sigma. And then we have we have temperature and pressure. So these two can just be this is the temperature and pressure of the system, which can be measured, and then the average molecular weight, or the molecular weight of A and B, that can also be found easily. And then this is going to be found mostly in a table. Then if we want to find the collision integral for diffusion, it's this one. It's going to be based on the boiling point of the system. And then this can be estimated by saying T star is equal to the Boltzmann constant times the actual temperature over the energy of molecular interaction between component A and B. So you would use this estimate to solve for the collision integral of diffusion, and that will give you your diffusion coefficient, and this is going to be for a vapor. So that's how you estimate the diffusion coefficient for vapors. And now we want to find the diffusion coefficient for a liquid. And this is going to be using the Stokes-Einstein equation. So we're going to have the diffusion coefficient of A through B. This is going to be infinite because this is used mostly in a dilute system. So basically the amount of component B is going to be a lot higher than the amount of component A. So that's why this is going to be infinite. So this is going to be the Boltzmann constant times the temperature of the system over 6 pi times the particle radius of the solute, which is going to be A, times the viscosity of the solvent, which is B. Okay, so this equation will give you the diffusion coefficient of a liquid, but sometimes you might not be able to easily calculate all of these variables. So in that case, you can use the Vignes equation. So this equation will give more of an estimate of the diffusion coefficient of A through B. It's going to be equal to the diffusion coefficient of A through B. It's going to be the infinite raised to the mole fraction of B, and then it'll be times the diffusion coefficient of B through A times the mole fraction of A. Or rather, sorry, raised to the power of the mole fraction of A. So for the most part, these infinite dilution coefficients are known. So raising them to the mole fraction of each component will give you a good estimate for the diffusion coefficient, which can be plugged into this original Stokes-Einstein equation to solve for variables like the radius or the viscosity. So now we're going to move on and derive an equation, a continuity equation for component A diffusing in a unidirectional system with the rate of formation Ra. Okay, so we have Ra is the rate of formation. And this is going to be per volume. So let's draw the system. We're going to have a cube. All right. Great. Okay, so going into the system, we have Na, and this is going to be on the z-axis. This is going to be z, dz, and then we're also going to have, I'll label the other axis as well. This is going to be y, dy, and x, dx. Okay. Okay. And then this will be flowing out. So this is going to be Na of z dz. And then if we remember other continuity equations, you know that in minus out plus accumulation. So with that in mind, we're going to have out, which is this here, Na z dz, times, it's going to be flowing through this face here. So that's going to be the cross-sectional area to it. That was dx dy, and then minus, oops, sorry, that's out. We need to do in first. So that's going to be NaZ times the cross-sectional area dx dy. There we go. And then minus out. And then plus the accumulation, which is in this case going to be the rate of formation. This is Ra. And then we said that was per volume. It's going to be dx dy dz. And then this is going to be equal to the driving force. So, like I've said in numerous other videos, the driving force is some type of gradient, and in this case it's going to be a concentration gradient. So it's going to be the change in concentration of component A times the volume, which is dx dy dz. And this is going to be over the change in time because it's a flux. Okay, so now we can simplify this. If we divide this term here, this volume, over here, so we're going to get that the molar flux of component A in over, it's going to be divided by dz minus the molar flux of A coming out over dz plus the rate of accumulation is going to be equal to the change in concentration of component A over the change in time. And this can be just simplified further by just putting this together. Okay. So both of these in minus out over dz. Okay? Okay, and then this term up here is if we factor out a negative, make that a negative, make that a positive, that's going to be the same as negative the change in the molar flux on the z direction over the change in position. I'm just doing this that way it's more simple. Plus the rate of accumulation is still going to be equal to the change in concentration of A over the change in time. And then if we bring all this to the same side, we're going to get that 0 is equal to the change in molar flux over the change in position minus the rate of accumulation plus the change in the concentration of A over the change in time. And then that's going to be pretty much the same as this well-known equation where it's going to be the gradient times the molar flux of A minus the rate of accumulation plus change in concentration of A over change in time. Those are the same. So that's our final continuity equation. And that's how you derive a continuity equation for component A diffusing through a unidirectional system with a rate of formation. Okay, so now we're going to move on and talk about equimolar counterdiffusion. So here we're going to have, let's say this is like a bubble, so this will be vapor, and then it's going to be in some liquid. And then here at this interface, I'll just highlight it. Okay. At this interface here, this is going to be at oops. This will be at vapor liquid equilibrium. Okay. So then at this interface, the liquid will evaporate. So it would be liquid to vapor. And this is going to absorb enthalpy. In the vapor phase, that's basically just absorbing energy. And then at the same time, we have vapor condensing to liquid, where it releases enthalpy. So it's exchanging, like this change of enthalpy from liquid to vapor or vapor to liquid is going to be the same. So this change from liquid to vapor and vapor to liquid is going to be kind of like a continuous cycle. So we're going to have that the molar flux of component A is going to be XA, because the liquid is going to be X, vapor is going to be Y, times the change in enthalpy plus the molar flux YA times the change in enthalpy is going to be equal to 0 because it's in equilibrium. And then, like we just said before, this change in enthalpy is going to be the same. So that means that the enthalpy of vaporization is independent of composition. So that's that. And then if we simplify this equation, we're going to have that the molar flux of the liquid component A is going to be equal to negative molar flux of the vapor of component A. So that's going to be this molar flux in the liquid phase is going to be equal to the liquid flux in the vapor phase. So that means it's equimolar. And then counter diffusion, we have one side positive, one side negative. Okay, so now what would this look like if the molar fluxes were not equal? So let's say for this example that component A is going to be equal to 2B, it's component B. So the overall flux equation is going to be that the molar flux of A plus the molar flux of B is going to be equal to the total molar flux. So the molar flux of B is going to be equal to negative 2 times the molar flux of A, because to get 1 molar flux of B, you're going to have 2 molar flux of A in the opposite direction. So that's where the negative 2 is. And then we can plug this back in here for NB. So we have the molar flux of A plus negative 2 molar flux of A is equal to N. So this is going to give us that N is equal to negative molar flux of A. Or the total molar flux is going to be equal to the negative molar flux of A. So then this is the relationship between the total molar flux and the molar flux of component A. In this case, they're equal and opposite. We can do this again for one more example. This will be a similar setup, but this time we're going to have 3A and 1B. Actually, before I do this, I'm going to explain how we get this negative 2 a little bit better. So if we set up a flux ratio of like Na to, or the molar flux of Na to the molar flux of B, we're going to have that Na is going to be over negative 1, and it's negative 1 because A is going to be a reactant, and then it's going to be equal to molar flux of B over 2, and the 2 is positive because it's a product. So if you multiply the 2 over and the negative 1 over, we're going to have that 2 times the molar flux of A is equal to negative molar flux of B, which is the same as what we got here. So using the same ratio idea, like the molar flux ratio, we're going to have molar flux of A over, this time it's going to be negative 3, because there's 3 moles in the reactant side. And it's going to be equal to the molar flux of B over 1, because there's only 1 mole of B in the product side. And then this will give the molar flux of A is going to be equal to negative 3 times the molar flux of B. And then since we want to solve for just the molar flux of B, we're going to get negative 1/3 times the molar flux of A. Excuse me. And then same as before, we said that molar flux of A plus the molar flux of B is going to be equal to the total molar flux. So doing that, we have molar flux of A plus negative 1/3 times the molar flux of A. It's going to be equal to the total molar flux. So this is going to be, this will be 3/3. We're going to have 2/3 times the molar flux of A is going to be equal to the total molar flux. So that's how we get that relationship.